Le Chatelier's principle, or Le Chatelier's principle, if you want to say it more properly. I usually shorten it down to Le Chatelier's principle. That's going to be the topic in this lesson, and super important concept in this chapter on chemical equilibrium. And it's very conceptual in nature, though. Not much for calculations in this particular lesson. The rest of the chapter will be very calculation intensive, but you can take a little bit of a breather on the math for this lesson. Now, if you've heard the terms like the equilibrium shifts to the left or the equilibrium shifts to the right, this is all about Le Chatelier's principle. That's what we're going to discuss in this lesson. Now, this lesson is part of my high school chemistry playlist. I'm releasing these lessons weekly throughout the school year, so if you want to be notified every time I post a new one, subscribe to the channel and click the bell notification. All right, so Le Chatelier's principle, and ultimately what Le Chatelier's principle says is that if you put a stress on a system at equilibrium, it will respond to counteract the stress. Okay, so we got to unpack that a little bit. So if you put a stress on a system at equilibrium, well, what is considered a stress? Well, anything that takes that system out of equilibrium, that's what a stress is. If it doesn't take the system out of equilibrium, well, then it's not considered a stress. So if you place a stress on a system at equilibrium, it will take it out of equilibrium. Well, the system's going to respond to counteract the stress so that it can get back to being at equilibrium. That's what Le Chatelier's principle ultimately says. Now, if we're going to talk about a system when it's not under equilibrium, as well as being under equilibrium, we need to define a new term, and that new term is called the reaction quotient. And here I'm going to call it Q. So, and Q, it turns out, equals the same ratio of products to reactants. The key is just when are we talking about that ratio? Well, that ratio for the reaction quotient is at any point in time. Doesn't matter. Let's get this right, though, in identifying our chemical species here. So at any point in time during the reaction, whether you've reached equilibrium or not, you can always call the ratio of products to reactants the reaction quotient. But if you recall, we said this ratio only equals the equilibrium constant if your reaction has actually reached equilibrium. If you're at equilibrium, well, that is the only time that that ratio actually equals the equilibrium constant. So keep that in mind. Now, again, this ratio, whether you're at equilibrium or not, always equals Q. And so sometimes we're going to see that Q and K will have the same value. And if that's the case, well, then you're at equilibrium. But if Q, the ratio that you actually have in your solution right now, doesn't actually equal the equilibrium constant value, well, then you're not at equilibrium. So that's kind of the deal. And so, again, we're going to be looking at stresses that take a system that has achieved equilibrium but take it out of equilibrium, which is why we need to talk about this ratio under conditions where it's not at equilibrium. So that's why we're kind of coming up with this. All right, so if we take a look at our reaction here, again, this is my favorite reaction, so we're going to talk about it again, and we're going to talk about the things that could take this system out of equilibrium. But let's say the system has reached equilibrium, and then we put a stress on it. And the first stress I'm going to consider putting on it is we are going to increase the concentration of O2. And so maybe we just dump a bunch of O2 or pump a bunch of O2 gas, might be the more proper way to say it, but pump a bunch of O2 gas into the vessel. And if we do that, the system's no longer going to be at equilibrium. And so we're going to take a look at this. So let's say that, this ratio of products to reactants has reached some constant value. And maybe it took a while to get there and stuff like that, but it's reached some constant value, and it's been constant for a little while now, and then we add a bunch of O2. And because we've added a bunch of O2, we're probably no longer going to be at equilibrium because it's going to change our ratio here. And a minute ago, this is the exact ratio we needed to be at equilibrium. But because we added a bunch of O2, that's going to make the denominator bigger now. And it's not going to equal the equilibrium constant ratio anymore. And so we can't call it K anymore. We'd have to just say it's the, what's the reaction quotient? So because the equilibrium constant doesn't apply to our situation. Now, the equilibrium constant value will not have changed. It just means that our system will not be at that equilibrium point anymore. So in this case, by adding more O2, my question is, what happened to the ratio? Did the ratio go up or did the ratio go down? Well, in this case, by adding O2, if we were just a minute ago at equilibrium, by adding a bunch of O2 at the instant that you add it, you just made the denominator bigger. And if you make the denominator bigger, you're dividing by a bigger number, your ratio just got smaller. And so what this ultimately does is all of a sudden, this just got smaller. The whole ratio just went down, and the very instant you pumped in all that O2, that ratio just got smaller. What you're going to find, though, is that the system's going to counteract that stress so that that ratio gets right back to the exact same value of the equilibrium constant. So that's Le Chatelier's principle. If you put a stress on a system, i.e. something that takes it out of equilibrium, it will respond to counteract the stress to get back to being at equilibrium. So that's what's going on here. So in this case, we have some terminology for it though. So if you notice, once we took it out of equilibrium, to get back to equilibrium, that ratio had to go back and increase in this particular example. So the moment we added the O2, we could say though that Q was less than K. Our ratio right here, at the moment we added the O2, we could talk about Q there, whereas obviously if you've reached equilibrium, that's your value of K right along the horizontal line there. And so the instant we added the O2, we can see, yeah, it went down. And so Q was less than the K value that we have for this reaction. And so by adding O2, Q is less than K. And so oftentimes we define things in terms of, is Q bigger than K? Is Q smaller than K? And that's why we're emphasizing this. So, but what we say regarding this reaction is that this is going to shift to the right, or that the equilibrium is going to shift to the right. And what this means is that we need to make some more products. So notice if we need this ratio to go back up, well, what we're going to do is we're going to turn some of our reactants into products. And that's going to make our denominator get smaller and our numerator get bigger, both of which are going to cause that ratio to go back up. So that's the mathematical way of looking at this, and some students like it and some students don't. So the more conceptual way to look at this is to talk about the stress itself. So what's the stress on our system in this example? Well, we have too much oxygen to be at equilibrium now. Well, then how do you counteract that stress? Well, you got two options. If you shift to the right, that means you have the reaction go in the right-hand direction, to the forward direction, and make more products, or you can shift to the left and make more reactants instead. So that's our options. Well, our stress is that we have too much O2 to be at equilibrium. If I shift to the right, I use it up. And that's going to counteract that stress. Notice, if we did the opposite though, if we shifted to the left, we'd actually make more O2. That wouldn't be counteracting our stress. Our stress is that we have too much O2. Making more doesn't help us, it hurts us. So that's kind of the idea with the Chatelier's principle being phrased like, if you put a stress on a system at equilibrium, it shifts to counteract the stress. All right, so what we've just learned here is that if you increase the concentration of a reactant, it's going to shift to the right to counteract that stress. So if we do the opposite then and increase the concentration of a product, the question is what's going to happen now as well. Well, again, we can look at this mathematically and say, okay, the instant we add CO, that's going to change this ratio. And so we're not going to be at equilibrium anymore. It's going to change it in some fundamental way. And the question is, when we add CO, so how does it actually change the ratio? So, well, in this case, if we add CO, we just made the numerator bigger. And so that's going to be a very quick increase in the value of the ratio, the reaction quotient. And then it's going to respond to lower that ratio back down to equal the same equilibrium ratio we've had the whole time here. All right, so at the instant you add the CO, then you've made the numerator bigger. So, and the entire ratio is therefore bigger. And so at that instant, Q is greater than K. So again, here Q has become bigger than that K value, the equilibrium constant value. All right, well, in this case now, the problem is not that you have too much O2, the problem is now you have too much of the product, too much CO. And so if you shift right and make more, you're not counteracting the problem, you're making the problem worse. And so to counteract the stress, this system is actually going to shift to the left, we say. And that's what any system will do when Q is greater than K. So when Q is less than K, a reaction needs to shift to the right to get back to equilibrium. When Q is greater than K, the reaction needs to shift to the left to get back to equilibrium. So that's one way of looking at it, again, the mathematical way. Or again, conceptually, you could just say, well, my problem is I have too much CO, so let's use it up and shift back to the left. Okay. Now, look at the opposite here. So let's say we actually lower the concentration of CO. So if we lower the concentration of CO, again, we've changed our ratio here, so we're not at equilibrium anymore. And by lowering the concentration of CO, we've lowered the value of the numerator, which means we've lowered the value of the entire ratio. And so at the moment we lowered the CO, again, that ratio just got smaller. And so at that very instant, we're back to a situation where Q would be less than K. And again, how's the system going to counteract that stress? By increasing that ratio back up so that we get back to being at equilibrium. All right, so in this case, you could look at this mathematically to say Q is less than K, so we need to shift to the right to make that ratio go up, and that's one way to look at it. You could also, again, conceptually say, well, what's the problem? Well, our problem is we're not at equilibrium anymore because we don't have enough CO. And if we don't have enough CO, how do we counteract that problem? Mix some more. And so another way to look at, yep, this needs to go in the forward direction again, and we say that this equilibrium needs to shift to the right. Okay, so big takeaways here. If you add a reactant, shift right. If you lower the concentration or remove a product, we say, also shift to the right. So just like we've done in the first and third one here. Now, if you add a product or remove a reactant, it would actually do the opposite and shift left, like we learned in the second example. Now, one thing we do got to be careful about, though, is like solids. And if you recall, solids do not show up in our equilibrium constant expressions at all. They have an activity of 1, and that's not going to change. And so in this case, if I can't really talk about changing its concentration, because again, solids don't really have a concentration in the same sense, but I could say add some carbon solid. And a lot of students would look at this and be like, oh, Chad added a reactant, so it's got to shift right. However, it's not true. This is not considered a stress, because if I was at equilibrium a second ago and we added carbon solid, well, then this ratio hasn't changed. And if this ratio hasn't changed, then we're just still at equilibrium and no shift going to happen. And so what we're learning here is that adding a solid is not going to shift the equilibrium at all. If it doesn't show up in the equilibrium expression, then it can't cause a shift. Okay, so first tricky part to this. Now, the last little parts are going to be dealing with pressure and temperature, and these are the ones that students struggle with the most typically. And so we'll start with terms of pressure. So, and if you look at changes in pressure, so if you lower the pressure, a gas expands. If you increase the pressure, a gas is compressed. Whereas solids and liquids are largely incompressible in comparison. I mean, it turns out solids and liquids can be compressed a teeny tiny bit when you jack up the pressure, and they might expand a teeny tiny bit when you lower the pressure, but not really in any measurable amount on the scale that we're talking. But gases, jack up the pressure, they get smaller. Lower the pressure, they get bigger. And so this effect, when we talk about pressure here, is going to be focused solely on the gases. And so in this case, I'm going to say increase the pressure. So, and there's one of two ways to phrase this. We could say increase the pressure. So, and usually the easiest way to increase the pressure on a system is actually to reduce its volume. So you could say increase the pressure, or you could say reduce the volume of the container, which would increase the pressure. Either way you want to say this is typically how you'd see it. So, all right, so if we increase the pressure or decrease the volume, what's this going to cause? Well, in this case, you're like, well, Chad, pressure and volume don't show up in the ratios. Why should this cause a shift at all? Well, they don't show up directly, but they do show up indirectly because these brackets, again, mean molar concentration, which is moles per liter, moles per volume. And so volume actually does show up in here indirectly. Okay, so in this case, by lowering the volume, you have all of a sudden, you have the same number of moles of your products and reactants, just in a much smaller space. And again, if molarity equals moles over the volume in liters, by lowering the volume, you just raise the molarity of everything. If you cut that volume in half, that would double the molarity of everything. Well, notice if you double the molarity on the bottom and you double the molarity on the top, they don't cancel out in this case because of that exponent of 2 right there. This would be doubled squared, and this would just be doubled on the bottom, and overall, Q would have just doubled in that case. Now, if you had the same number of moles of gases on the reactant side and the product side, and it turns out that you wouldn't experience a shift. But because there's not the same number, you will experience a shift. And it is ultimately a change in molarities in all your species. All right, so increase the pressure, decrease the volume. In this case, you can think of this conceptually in terms of the size of a mole of gas. You learned in the gas chapter that 1 mole of any gas at STP has a volume of 22.4 liters, if you recall. And so in this case, on the reactant side, we have 1 mole of gas. Solids take up way less space, and we'll ignore them. So, but on the product side, we have 2 moles of gas. And so under the same conditions, the products would take up twice the volume as the reactants. And so in this case, if you're increasing the pressure by decreasing the volume, that means we have less space available. And so the stress is that we don't have enough volume anymore. We don't have enough volume to be at equilibrium. So there's not enough space around. Well, we can shift towards the direction that will take up less volume, the side with fewer moles of gas. In this case, 1 mole of gas, again, compared to 2 moles of gas. And again, ignore anything that's not in the gaseous phase. And so by increasing the pressure, it favors the side with fewer moles of gas. And again, I like to usually look at this in terms of volume. Pressure and volume are inversely related. So increase in pressure, decrease in volume. Lower volume shifts to lower moles of gas. That's the way it works. If you got a lower volume, well, lower moles of gas would take up less space and be perfect for that. And so in this case, we're going to end up with a shift left. Yet again, but again, keep this in mind. If we lowered the volume, let's say we cut the volume in half, again, that would double all the concentrations. And if you double the concentration in the denominator, double the value of the denominator, but again, doubled squared here would quadruple the numerator. And so 4/2 would mean Q just doubled. And so that would mean that Q just went up. And again, it's going to try and reduce that ratio back down to the same value of equilibrium constant. That's what's going on here. So let's get that back up there, Q. And so at the moment we jack this pressure up by reducing the volume, at that exact instant, we see that Q would be greater than the equilibrium constant value. Q is greater than K. And then once again, when Q is greater than K, we've got to shift to the left to get back to equilibrium. Okay, the trickiest one on here typically for students is involving temperature changes. And unfortunately, I can't ask you about a temperature change yet unless I give you one key piece of information about this reaction. And that key piece of information, it turns out, is delta H. If I don't tell you delta H, I can't ask you anything regarding temperature in Le Chatelier's principle. But in this case, let's just say I tell you that delta H is negative 100 kilojoules for this reaction. I have to give you that or else, again, I can't ask you the next question. But now that I've told you this, so we can now ask you about temperature changes and how they affect the equilibrium. Now in this case, I told you that delta H is negative. So now for this one, I don't know the exact value, but I would know it's negative. This is a combustion reaction. Combustion reactions release tons of heat. I'm not expecting you to have anticipated that here, so I'm just trying to make it make sense for you. But in this case, delta H is negative means it's an exothermic reaction and it releases heat. And because it releases heat, we could say that it produces heat. We could say that heat is a product of this reaction. And in fact, we could just write it as another product in this reaction. And so notice, it doesn't really matter if you add heat or remove heat from the system or something like that. That's not going to change whether it's a reactant or product. Whether it's a reactant or product is totally dependent on the value of delta H. If delta H is negative, making the reaction exothermic, heat's a product. So if delta H had been positive, that would mean a reaction is going to consume heat. It's going to use up heat. That would mean heat would have had to have been a reactant instead. And so for an exothermic reaction, heat's a product. For an endothermic reaction, heat's a reactant. And so in this case, I can talk about raising the temperature or lowering the temperature. And we'll start with raising the temperature. Let's say we increase the temperature of this reaction here. So by raising the temperature, we're adding heat. If we lower the temperature, we're removing heat. And so in this case, a lot of students think that if you're adding heat, then you're adding a reactant. Well, again, whether or not heat is a product or reactant of the reaction is not about what you're doing with your temperature down here. It's about whether the delta H value is positive or negative. And again, with an exothermic reaction, delta H is negative, heat is on the product side. It's a product of the reaction. Now, in our case, by raising the temperature, we're adding heat. And by looking back at the reaction, though, we now realize that we're adding a product of the reaction. This reaction produces heat. When it reacts to the right, it produces heat. And so if we add more heat, the problem is now we're going to have too much heat present to be at equilibrium. And how do we counteract that stress? We shift to the left to use up that heat. If it's an exothermic reaction in the forward direction, it would be an endothermic reaction in the reverse direction. And so again, if we've raised the temperature, well, now there's too much heat around. So how do I counteract the problem of having too much heat around? Use it up. Shift left in this case. And so key to predicting a temperature effect is to figure out if your reaction's endothermic or exothermic first so that you can decide whether or not heat is a reactant or a product. And then you can say, well, if you're increasing the temperature, you're adding heat. And then you have to figure out, are you adding a reactant or adding a product, again, based on whether it's endo or exothermic. Had we lowered the temperature, then we'd be removing heat. And again, you'd have to figure out, am I removing a reactant or removing a product, based again on whether it's endo or exothermic. Okay, now this last one is special. So because notice, heat does not show up in this ratio at all. And so at the very moment you add that heat and raise that temperature, this thing just stays constant. Hasn't changed at all. So aren't we still at equilibrium, and wouldn't this not be a stress? Glad you asked, and no. That's my trick question. We're not still at equilibrium. This is a stress. If you recall, we said the one thing that can change the value of an equilibrium constant is a change in temperature in the last lesson. And so this, for all these other shifts, we ended up getting back to the same K value after the system had time to counteract the stress. But this is the one time where we've changed the temperature now, and it doesn't actually change the ratio at all. So, however, it changes the target value for the equilibrium constant. And so it turns out for an exothermic reaction here where heat's a product, if you add more heat, it shifts left to get to the new value of the equilibrium constant. And shifting left means we're going to turn products into reactants. And so it's going to use up products, lowering the value of the numerator, and make more reactants, increasing the value of the denominator. Overall, that's going to lower the value of this ratio. And what we're going to find, and I'm going to go back in time just a second here, what we're going to find, though, is that this system's going to respond to get to a new horizontal line. So our new K value is older than our lower K value. So whatever you do with temperature is going to actually be the one thing that can change the value of the equilibrium constant. And in this case, if whatever you do with temperature causes a shift left, well, that means at the new equilibrium, you're going to have more reactants than you just did a second ago, and less products. And overall, this is going to be a decrease in the value of your equilibrium constant. So with whatever you do with temperature, if it causes a shift right, then you end up with more products than you did a second ago, and that would increase the value of the equilibrium constant. So, and again, this is the trickiest one, especially pressure and volume both, but pressure and temperature both, but temperature especially. Cool, that's Le Chatelier's principle. If you found this lesson helpful, would you consider giving me a like and a share? Again, pretty much the best thing you can do to help make sure other students get to see this lesson as well. If you are looking for practice problems on Le Chatelier's principle or chemical equilibrium at large or anything in your high school chemistry class, check out my premium course at chadsprep.com.